be a fuzzy subset of Y. What is the inverse and inverse image? Again, instead of sets, we work with membership functions. This is the definition of membership function for F mu and F inverse lambda. So this definition is related to this ordinary case. Or for example, you know in ordinary set theory, we have similar equality like this. But here, these are physicals.
Sorry.
Yeah.
Can you explain why supremum?
Supremum. Since in intersection and union, our definition related to maximum and minimum, yeah? So when our set be a family of sets, instead of maximum we use supremum, instead of minimum we use it.
For the previous reason.
Since when you can't, our function may be not be one-to-one. One-to-one, yeah? So maybe exist several elements go to one element, yeah? Between them, we consider the sup or max. When we consider its universal set and a fuzzy subset of its, when we say mu a its, always mu a its plus equal to 1. In intuitionistic case, we consider two functions. One, this function we say membership function. And another function, non-membership function. So, when lambda be mu complement, lambda be mu complement, intuitionistic quasi sets will be ordinary quasi sets. In other case, sometimes in real, maybe the summation of mu x and lambda x less than 1. For example, again, repeat the first example, yeah? We say mu a X3 is this number. Yeah? So, in ordinary case, mu AX complement is this. Yeah? But in intuitionistic case, we say this. Mu A x3, for example, 0.7, lambda A x3 0.1. So, related to this, we are not sure the numbers, these numbers related to this case belonging or not belonging. This case we are not sure. Usually intuitionistic quasi-sets used in medical cases. Again, if we consider this, it's important to know about the union in. This is Atanasov, the first one that introduced the notion of intuitionistic fuzzy sets. He is from Bulgaria. Here you see the definition of intersection, complement, union, and some new operation. For example, here, for complement, it is necessary we change membership function and non-membership function. In lambda A, mu A, we change them. For intersection, for membership function, we use the minimum. For the non-membership function, we use maximum. For union, again, for membership function, we use maximum. For non-membership function, we use minimum. Also, you know, this interval is a lattice. Yeah? If you're now familiar with the notion of lattice, 0 and 1 is a lattice. One of the generalization of fuzzy sets is substitute a lattice L instead of 0 and 1. Okay, I think this elementary introduction was useful for you. This is the first part of my talk. If you have any question, you can ask, or not, we can give you rough sheets. Again, let U be a universal set. You know equivalence relation, yeah? Equivalence relation means through it. Sometimes maybe we write this x belong to rho. Symmetric condition. If we consider this, the equivalence class of this. Will be all of y such that y rho in basic mathematics, you know with every equivalence relation, we obtain a partition, yeah? And with every partition, we obtain equivalence relation. I don't know Indonesian name of this book. Maybe if the students know the meaning of this in Indonesia, now better. All of x such that the class of x is a subset of A. For upper approximation, we consider intersection. I have a picture to show you this. Look on this picture. This is U. With rho and equivalence relation, we obtain partition, yeah? Suppose that these are partitions. So, for example, every square is one class. Every square is one class. So we consider a subset of U. You consider red picture the A. Okay? First, we want to determine lower approximation. Lower approximation are all of x such that the class of x exactly inside A. So the green squares exactly are inside our picture. So the green squares will be lower approximation of A. For upper approximation, we consider the classes that have intersection non-entity with A. So not only with green parts, but also white parts together. With the upper approximation. So always A is between if you are familiar with topology, this is similar to interior and exterior of sets in topology. Also similar to fuzz sets, this theory have many applications in different areas of science. For example, Davvaz the first person that introduced the notion of lower and upper approximations and rough sets was not a mathematician. He was an engineer. Because of some problems in control theory, he introduced these subjects. Also, the difference between upper and lower approximation is called boundary region. Boundary region of A, difference between the upper and lower approximation. So that in our picture, this will be white part in the picture. If we show boundary region with this notation, when a subset X of U, we say is definable, X is definable when lower and upper approximations are equal. If X is a subset of U with a predicate P, we say X belongs to lower approximation. This means that it certainly has property P. When we say X belongs to upper approximation, this means that its possibility has property P. Here you see some elementary results between lower and upper approximation. For example, A always between lower and upper. If A be a subset of B, lower A, subset of lower B, upper A, subset of upper B, and also some results related to, for example, union or intersection. You see here, lower approximation of A intersection B is equal to this, but for upper approximation of A intersection B is a subset of upper approximation of A intersection B. But this is not a subset of this in general case. We can consider an example to show the converse is not true. We can consider a function, approximation function, from power set of U to power set of U plus power set of U. This function assigned to every X lower and upper approximations. We say this couple is a rough set if we find define it such that and similar to was the case, we must define operation between rough sets, union, intersection, complement like this. I explained in the slides, but since I have not time, I'm going to explain about operation between them. For example, in this slide, you see the definition of union. Definition of union. For the union of between rough sets, we use this symbol. This is equal to this and this, and also intersection when time rough sets is a subset of others. These are some results related to abstract algebra. I don't want to talk about them. Only I want to discuss about a simple using of these notions again in algebra. Again, suppose that so rough sets and algebra. You know, in algebra, normal subgroups are so important. We use this notation for normal subgroups. G over N, the set of quotient. If you be familiar with algebra, if this B, G, with normal subgroups, cosets, again, make a partition for G. So, instead of equivalence relation in a group, you consider normal subgroup. Now, if A be a subset of G, related to N, such that and if instead of group we consider a ring, instead of normal subgroup we consider ID. Then again, if A is a subset of R, some elementary questions here. Maybe one person asks if you consider A subset of G. If A be a subgroup of G, if A be a subgroup of G, whether lower or upper approximation of A again is a subgroup of G or not. If A be normal, again, whether lower or upper approximations are normal subgroup or not. Similar questions here about ideals. If A instead of subset B an ideal of R or a subring of R, then whether lower or upper approximation of A are subring or ideal or not. Many years ago, I worked on these subjects, I think, till prime ideals and primary ideals I worked. When type if A be prime ideal of R, when lower or upper approximation are prime ideals, or primary ideals. Sorry to disturb you for a long talk. Only I show you one similarity between these notions and conditional probability. Now, before I explain about this, I mention one of the, you studied probability, yeah? Now today, you listen me about fuzzy sets, yeah? If a person asks you what is the difference between probability and fuzzy sets, explain one of the difference. Exists many differences between them, but explain one of the difference between them. In probability, always the sum of probability is equal to 1. In fuzzy sets, maybe the sum of membership function be so bigger than 1. About,